So here we are, chapter 19, talking about fossil fuels. We just finished up on talking about climate change, much of which is caused by humans' use of fossil fuels. So we're going to dive into the different types of fossil fuels, how they're formed, how we use them, what the consequences are, all of that. So basically, humanity has devised many ways to harness the renewable and non-renewable forms of energy on our planet. Remember that renewable means that it can remake itself, and non-renewable means that there's a finite amount that will run out. Here's a little chart of the differences. So we have coal, oil, natural gas, natural energy, biomass energy, hydropower, solar energy, wind energy, geothermal energy, tidal wave and energy. So these up at the top are grouped as non-renewable. So the first three are fossil fuels. They are labeled as non-renewable because fossil fuels could continue to get made, but it takes hundreds of millions of years, and we're using them so fast that there's no way that they are making at the same rate at which we are using them. So this is a good little table in case you get stuck on what the different types of energy are. So they are there. So nature offers us a variety of energy sources. Most of the Earth's energy comes from the sun, which drives wind, the water cycle, and photosynthesis. So basically, the sun is where all of the energy on our planet has come from. We can use solar power for electricity. We can harness the actual sun's rays, but also solar radiation drives wind power and water power, which we can also, or hydropower, which we can also harness for energy. And also, obviously, the sun, solar power, solar radiation powers photosynthesis, which is where all of the fossil fuels and biomass that we're burning come from, or wood also and biomass. So when plants and animals die, when plants and other organisms die and are buried in sediment under particular conditions, so they die, they get covered under very particular conditions, and we'll talk about what those are. They're stored chemical energy, so all of the glucose and everything that's stored in the bonds in your cells, remember that chemical bonds store a lot of energy between them, it's all may eventually be incorporated into fossil fuels, such as oil, coal, and natural gas. Those are the big three: oil, coal, natural gas. Other forms of energy on the Earth include geothermal energy from the Earth's core, as well as the bonds between protons and neutrons in atoms. Energy sources like sunlight, geothermal energy, and tidal energy are perpetually renewable. Tidal energy is the energy of the tides in the oceans, and that is also powered by the gravitational pull of the moon and the sun. Sunlight is never going to run out unless the sun explodes. Geothermal energy will never run out. Tidal energy will never run out unless the sun or the moon go away. So those are perpetually renewable. We can keep using them without depleting them. Coal, oil, and natural gas are considered non-renewable because it takes thousands of years for the biosphere to generate the organic matter consumed by our society in a single day of fossil combustion. So the amount of fuel that we use in one day as a society would take thousands of years to make. So that's why they are non-renewable. At our current rate, we will use up the available fossil fuels that the planet has in just a few decades. So that's a lot. And because of this, and because fossil fuels exert severe environmental impacts, which we'll talk about, renewable energy sources are increasingly being developed as alternative to fossil fuels. So we're going to look also at alternative energy sources, a little in this chapter, a lot in next chapter. So as a society, we rely mostly on fossil fuels. Since the Industrial Revolution, fossil fuels have replaced biomass as our dominant source of energy. So before that, we were just burning fuel, burning wood and other living things for energy. And there's a lot of it's very high energy content, so it makes it efficient to burn, ship, and store. So if we're going to pay to get some energy here, fossil fuels have more energy stored in them, so it's cheaper to transport them. A single gallon of oil contains as much energy as a person would expend in nearly 600 hours of human labor. So it is very, very energy full. And that I wouldn't want to work 600 hours doing some sort of manual labor. So we'll happily take a gallon of oil. We use fossil fuels for transportation, manufacturing, heating, cooking, and to generate electricity. I'm covering electricity there, but electricity is a secondary form of energy that is convenient to transfer over long distances and apply to a variety of uses. So when I plug my computer into the wall, there's not like a little thing of fossil fuels in there powering my computer. It has been transferred into electricity at a power plant, and then it's easy to get through wires to get here. That's what electricity is. So we have the three different fuels, oil, coal, and natural gas, and it shows the levels of combustion for them and over the years. And each fuel has its own mix of uses and contributes different ways to our economies and our daily needs. So we use oil, coal, and natural gas in different ways. We use oil mostly for transportation and coal mostly to generate electricity. So around the world, these fossil fuels are unevenly distributed, as are so many things that we've talked about. I feel like I've said unevenly distributed in every chapter. And it varies from region to region, depending on which fossil fuel it is. So, for example, most of the coal reserves are found in the US, then Russia, then China, whereas most of the oil is found in the Middle East. Half of the world's oil lies in the Middle East, and then the Middle East is also rich in natural gas as well as Russia. So, and the US has the most coal of any nation. So it's spread out completely differently around the planet because of the way that these different things are formed and the different conditions necessary, which we will talk about. And then we can distinguish between how much we use energy. That also varies from place to place. Ooh, look at that graph. Per person, the most industrialized nations use 50 times more energy than do the least industrialized nations. So that graph is showing us that it's saying energy consumption per capita, so per person, and that's metric tons of oil equivalent. But basically, 6 is the high range, and the US and Canada are there. So is Saudi Arabia. That might be what that is, and it looks like Norway as well, or Finland, or Sweden, one of them. So the U.S. has only 4.4% of the world's population, but it consumes nearly 18% of the world's energy, which is staggering. So societies also differ in how they use energy. Developing countries tend to use energy for subsistence activities, so like to live, you're going to use energy to cook your food, to get from place to place, just to be able to survive, while developed countries use it for transportation, industry, and other uses. A lot of developing countries also rely on manual labor or animal labor energy sources instead of automated ones. And for example, most rice farmers in Southeast Asia plant their rice by hand, whereas in the US, industrial rice growers use airplanes to plant their rice. So here's how we use in the US use different types of fossil fuels and what we use them for. So oil is the biggest one. We have natural gas, coal, nuclear energy, which we'll talk about, and renewables, and where they go to. So oil is the most, then natural gas. Oil goes largely to transportation, but also to a big part to industrial. Natural gas goes a lot to industrial, and then a lot to electricity generation. Coal goes almost exclusively to electricity generation. Same thing with nuclear. Renewables are the kinds of sources we'll talk about, like wind power or solar power, and where they go. And so then electricity is what powers some of industry, most of commercial, and most of residential. What's over here shows the amount lost as heat, because remember that when we transfer energy between states, we lose, second law of thermodynamics, we lose some to the universe. So this is the energy loss. So you can see the amount out of the whole entire thing. So there's most of oil is lost. Car engines and fuel engines are very inefficient. We lose most of the energy. And then if you think about it, if your car is idling, like you're not moving and it's just stopped, think of how much the car itself is even moving, or like all of the things that are happening, and or how hot cars get. That's energy lost that doesn't get us from place to place. So industrial doesn't have as much loss. Commercial, maybe a third. Residential, maybe a third. Electricity generation, also a large amount lost to heat. So it takes energy to make energy. So if we're going to have energy available at our fingertips, we're going to need to put in some work. So harvesting energy requires the use of heavy machinery, construction of roads, pipelines, waste ponds, storage tanks, and more, all requiring investments of energy. And net energy is the difference between the energy returned and the energy invested. So how much energy are you getting out after you account for what you put in? So how much more energy do you have than what you started with? So that's net energy. Net energy equals energy returned minus energy invested. So the energy we get minus the amount we had to put in to get it. We also use this thing called the EROI, I'm just going to call it the EROI. It's called energy returned on investment. So it's calculated by the energy returned divided by the energy invested. So basically how how efficient is it? How much energy are we getting for the amount that we're putting in? It's a ratio, so it's like a percentage, so it's more valuable in that way. So ratios rise when extract the AROI. So high AROI means that we have received more energy from each unit of energy that we invest. Fossil fuel AROIs have been historically high, but the ratios can change over time. The ratios will rise when extraction becomes easier or more efficient, so you have to put in less energy to get the same amount out. So the return on investment, like the percentage you're getting out, is higher. And they will drop when resources become depleted and harder to extract, so we have to put in more time and more money to get the same amount of energy out. In the US, the AROI ratios for conventional oil and natural gas declined from 24-to-1 in the 1950s to 11-to-1 today. So that means that we used to be able to gain 24 units of energy for every unit of energy we put in. So I'm going to put in 1 unit of energy to get 24 out. And now it is, I'm going to put in 1 unit of energy to get 11 out. The AROI for discovery and production of oil and gas have declined because we found and extracted the easiest deposits first. We're going to take out the ones that are closest to the surface, easiest to get out, and so we're going to get a lot for not a lot of energy. But now that we've already taken out all the easy ones, we have to put in more money and time to get out the ones that are deeper and harder to find to get the same amount out. So where will we turn for energy? So enormous amounts of energy, money, and technology are now being used to extend our reach for fossil fuels. Fossil fuels have powered our advances in civilization and brought us to a standard of living our ancestors could scarcely have imagined. Think about any TV show or movie you've ever seen where someone from the past comes to the future and they're like, what is this light? What is this computer? What are any of these things? And now technology is advancing like crazy, but even having indoor lights or cars that move on their own, like that would be crazy to people who weren't around before then. So we have really changed our society because of fossil fuels. And so now we have to extend our reach for them. So oil and gas wells are being drilled deeper and into places that were once unreachable. We'll talk about this in a bit, but Arctic seabeds farther offshore in the ocean. So now we're having to go further and further out because we've already taken all the ones that are closest to us. And we're also having to look for new resources, such as oil sands, which we'll talk about. And so we're digging into new sources because we're running out of the ones that we had. Okay, let's talk about how we make fossil fuels. So fossil fuels were formed hundreds of millions of years ago, normally from about 100 to 500 million years ago, from organisms performing photosynthesis. So energy originated with the sun and was converted to chemical bond energy by photosynthesis. And most organisms will not end up as fossil fuels. The grand majority of all life that's ever been on Earth did not end as a fossil fuel because most will undergo aerobic decomposition, meaning that they will be decomposed by microorganisms in the presence of oxygen. They'll be broken down into simpler carbon molecules and then recycled into the ecosystem. That's that decomposer piece that we learned about in the different food webs and in the different cycles. However, some fossil fuels, after they die, will end up in an anaerobic environment, meaning that there's not a lot of oxygen, little to none, where their organic matter was converted by heat and pressure to a fossil fuel. So this happens a lot at the bottom of lakes, at the bottom of swamps, or shallow seas. So for example, this woody terrestrial vegetation, a tree, dies and falls into a swamp. Then what happens is it's covered by water, so there's and sediment, so there's not a lot of oxygen down here. So it's partly decomposed by microbes under accumulating sediments, and kerogen forms, and then eventually the kerogen under deep heat and deep pressure will alter kerogen. You don't need to know about kerogen, into coal. Or phytoplankton and other marine organisms will die and sink to the ocean floor. They're covered by sediments, and then organic matter from soft-bodied sea life is partly decomposed by microbes under accumulating sediments. Some carbon bonds are broken and the kerogen forms, and then this says that thermogenic natural gas is formed from kerogen. So different kinds of fuel will form based on where they are, and so basically there just needs to be, they need to die and be covered and have no oxygen available.